Please.
I have been working on a feature logo. I have the digital logo. Basically, if any of you use Matplotlib, play with it.
Thank you so much. Yeah, and it's always good to collaborate and have, have a more than one idea.
I might just get lazy and chip it in at the end.
Yeah, that's perfect. And there's always good to have more than one design. Often we, in the end, settle on some kind of a hybrid design. Okay. And the final thing that I wanted to announce that Mark Boak is here, Dirk organizer. So if you don't know Mark, there's Mark. He's also contributed in a very key way to getting the program in this wonderful way. Welcome, Mark. Okay, and without further ado.
Okay. So thank you. So one lesson learned from yesterday's talk is that never give lecture from your PDFs, because apparently the font is too small and you miss a lot of things. So has anyone taken a look in the website in the lecture notes? Good. Okay. So I guess not many of you have noticed that he had homework, as I have also missed. So the major improvement for this is I made notes of my notes, and this is what I'm going to teach from. The homework assignment was essentially vague enough to necessitate some thinking, and it was construct the compatibility conditions for the splay-free bend in a nematic liquid crystal. Yes.
So can you just remind us why? So I remember when you said, okay, now we're going to look at splay-free situations, but what was the motivation of that?
The motivation was that we had some liquid crystal, say a nematic liquid crystal, that had some internal structure, and the internal structure favored some bend, or bend in an absolute value, as I was corrected by Leo. So you would like to assume a constant bend. And other than that, you have the otherwise unaltered Frank energy, which penalizes splay. So I didn't want you guys to work out the whole thing. It's too laborious. But you could think of doing it in the non-splay free conditions. Okay. So what we started from was the fact that if the director field is cosine theta, sine theta, we could write the splay as minus, this is disintegrating, the splay is minus sine theta, theta x, plus cosine theta, theta y, whereas the bend is given by cosine theta, theta x, plus sine theta, theta y. And we can invert these relations to have theta x be equal to minus sine theta s plus cosine theta b, and theta y be cosine theta s plus sine theta b. Our compatibility condition was theta xy equals theta yx. That is the condition under which this equation makes sense. Now we obviously have derivatives of theta. onto which we're going to input the equations back. Okay, now this is going to lead us to an equation that doesn't have any derivatives of the angle theta, but there's a caveat in that, and it is assuming that these equations hold. So what we will end up with is a necessary condition, but not a sufficient condition. This necessary condition looks as follows. Just to give you one of these, you differentiate this by y, so you get one term which is cosine theta, theta y. Theta y has a cosine in it and an s. So you would have cosine squared and an s squared. You would have another s squared from this term, which eventually will lead you to this equation. I don't want to spend time on the algebra. It is s squared plus b squared plus n dot grad s minus n cross grad b, and this should be understood in the 2D sense. And in the 2D sense, I mean s squared plus b squared plus ny sy plus nx sx minus nx by plus ny bx. This has to vanish. This is an equation that every splay field and bend field of a general director have to satisfy. Now we immediately see from this one thing, which is if all derivatives vanish, this one goes, this one goes. The only possible solution is the trivial one. So we have already learned something from this equation. But there's one thing which is quite problematic in this equation. Nx, for example, is cosine theta. So this equation contains quite explicitly the field whose existence we're trying to establish. So that's a problem.
Can I just ask this
Yes.
director field that you have in the upper left has a singularity at the origin? Or it's a hedgehog? Or what is it?
I'm not dealing with singularities presently.
But you do have
No, this is a general theta is a function,
an arbitrary.
arbitrary function of x and y. This is only for normalization reasons. This was used only to make sure that n is a unit vector.
Sorry, missing something else. It looks like it's radially outward.
No, this is a general theta.
Right. I see.
Theta could be theta naught cross throughout space.
Coordinates of the two-dimensional.
Yes. Yes. There's no direct relation between theta, x, and y. Yeah. Thank you for that clarification. So this theta is the angle which is determining n in every point in the space.
This is just encoding that's a unit vector.
Yes, that's what it's encoding.
Could be a constant.
Could be a constant, for example.
Good. Thank you.
So this is useful, but it's not a compatibility condition. What I was hoping some of you at least do home is say, well, what happens if we take a simpler problem and ask, what happens if we try to throw out all the splay terms? What is the most uniform bent configuration we can cook up? Okay, so we're trying to have a uniformly bent no splay. What is the most uniform bent we can have? And for this reason, we throw this guy out, and this guy out, and we end up with these guys. Let's divide by b squared and call b to the minus 1 eta. So what we'll have now is 1, I just divided by b squared, plus cosine theta, that's an x, minus by over b squared is eta y, plus bx over b squared is a minus eta y. Yes.
So, when you threw out the Wisconsin S,
Yes, I'm assuming now, for simplicity, that S is equal 0. For a constant B. Yes, B is now not a constant. And you're correct that if we're now going to substitute constant B, we're going to get 1 equals 0, meaning we obviously did something wrong. Okay, and we can see it here. If we're going to substitute, all derivatives vanish, we're going to get B squared equals 0. So this is reproducing yesterday. Now we're allowing spatial variations for B. This guy. Yes, thank you. Okay. Now we can, for example, write this as 1 plus cosine theta eta y equals y minus cosine squared theta eta x. Square the whole thing, get a quadratic equation for cosine theta. It's in my notes. I'm not going to burden you with this, but essentially you get cosine theta as a function of eta x and eta y. And you get sine theta as another function of eta x and eta y. You take these two, and now remember that I told you we have implicitly assumed that these two equations hold. We have to substitute those results back into here. What we would get, so this is, for example, cosine theta derivative by x. So cosine theta derivative by x, we're going to get second derivatives of this function eta. And if we carry this whole thing out, we're going to get 2 PDEs in eta, which do have, a single PDE would be more convenient. The fact that you have 2 really narrows down the space of solutions, but they do still have solutions. I'm not going to go through them now. But for example, you could show that a band which goes as 1 over r is a solution to this problem. You could think of now as carrying out most of these steps even in the non-splay free conditions. And the general question we ask is, we have the local tendency of the material. It would like to assume a certain bend, a certain splay, and in 3D some certain twist. Can it achieve all those 3 simultaneously? What is the closest you can do to achieving those 3? Questions so far? Okay, so except for those homework, yes.
So we had bend and splay, and we said there was an issue with it because we had explicitly named theta.
Yes.
How does eliminating splay help?
No, it just made things algebraically simpler.
Oh, okay. So we
It had nothing to do with the conceptualization of the system. So it just made things algebraically more tractable, and because it was sort of homework, I meant to do it. Okay, so this brings us to today's topic, which is the elastic theory of frustrated bodies. And before we start, I would like to give you a few examples of residually stressed or frustrated elastic objects. And these are surprisingly more common than you would think. So how many people here have a smartphone? Okay, how many people here know what's the name of the glass in the front of the smartphone? Gorilla Glass. So it's a Popea toy by Corning, and apparently they're the only ones that are able to make such high quality tempered glass so thin. They do it by chemical methods, but essentially it's tempered glass almost like any other tempered glass, like the glass on the sides of our car, like the glass in some of the windows and doors here. So what is tempered glass? Tempered glass, surprisingly, can be understood completely mechanically. The tempering process strengthens it against failure, against brittle failure, but also gives it another property, which is the reason why we desire this in the side windows of our car, which is when it does break, it doesn't leave behind large shreds. It just kind of breaks to tiny little pieces. Now, in order to understand how tempering is able to perform both of these tasks, essentially strengthen against failure and make sure that if things does break, they break into small pieces, we have to understand what tempering does. So a tempering of a glass is a two-step process. In the first step, you heat the glass up until it flows almost, but you heat it above its transition temperature. Let's keep that hidden for the time being. And then, by using forced air, you cool it down abruptly. What you essentially do is you solidify the circumference of your glass piece. Now you let it cool down. As it cools down, the outside has already solidified. It preserves its shape. But because glass has a very non-negligible expansion coefficient, as it cools down, it shrinks. However, the inside, which now shrinks down, has to remain connected to the outside. So now you have a very small interior connected to an already solidified exterior. What the thing does is it pulls on the exterior boundaries while tensing the interior. Okay? The tensed interior flows to accommodate this until it's smooth enough. Sometimes it will even cavitate, but usually would not. And then it stops. So in the fully relaxed, in the fully solid state, after it has completely cooled down, you have a very, very compressed outer boundaries and very tensed interior. Brittle failure occurs when cracks are able to propagate through your material. In order for cracks to propagate, they have to have tensile stress to eat up. If I now throw a stone at this thing, and I would like a crack to propagate, the first thing it has to overcome is the enormous amounts of compression the boundary has. Only then can this deformation or stone throwing induce tension, which will be large enough to break this thing. If, however, you expose the tensed area inside, it's already under so much tension that it essentially breaks itself up. And the amount of energy stored in that tells you how big your pieces are going to end up being. How much, essentially, surface area, additional surface area you're going to produce when you break up. There's a very violent, very fun exemplar of a residually stressed glass. It's called Prince Rupert Drops. It's named after a Bavarian prince of the 17th century, but it dates back at least 100 years before that. You obtain these guys by just dripping hot molten glass into a bucket of water. I was trying to get some specimens for you here. Apparently, it's more complicated than that. When I did that, they shattered on impact. But I do not know yet the secrets of the trade. But when you do it correctly, you get a tadpole-shaped object, which solidified very fast on the contact with water while having had very, very hot inside. You can see some droplets or some bubbles in the inside, meaning this thing actually cavitated. Tension was so great while this thing formed that it made a small bubble inside of it. Okay. When yes, it points upwards, and you can see that by the fringes here, which is just in a polariscope, that the residual stress actually extends into the tail. So the inside is under tension, the external area is under compression, throughout this thing. If I hit with a hammer the top of this tadpole-shaped object, it's going to be very, very resilient. However, if I expose the tensed area, even if it is in the tail, which is relatively thin, so I can imagine just breaking it off, it's going to disintegrate. It is so residually stressed, it's going to actually pulverize. This is taken from Smarter Every Day on YouTube. I highly recommend to those of you who don't know it. Yes.
What was the perturbation? What did he do?
The perturbation, you say? So he hammered it with a, I think this is a diamond cutter, and then he just cut the tail. And of course, filmed it with a Phantom. Okay. So this is one, yes.
So I've heard it said that Gorilla Glass is a snake that is rigid but
So my education about Gorilla Glass came from, I think, their executive engineer coming to Chicago and telling us how they make it. And what I understood that in the production process, the first thing is they are able to make it super thin by dripping it in a special way and having it solidify as it falls down and taken somewhere else. And then what they do is they chemically exchange atoms on the boundary. And they show that the atoms they exchange for essentially induce elongation of the boundary. I think, okay, we can, yes. It is surprisingly flexible. I mean, I held one of these specimens when it's not in a phone in my head, and you can bend it significantly, but I think it is residually stressed, but we can discuss later. Okay, so the other case is a bit less dramatic. You can just pass these around behind you. There's not enough for everyone, but I think you actually did this at home more than once. You do this. You tear a piece of a plastic sheet. Okay, so it's a very simple action. And then you look at the boundary of this thing. And what's important to think of is, what are the symmetries of this process? Okay, I have this thing. It's planar to begin with. There's an up-down symmetry. My action here, which is pulling it at the boundaries, preserves this up-down symmetry. Okay? The only thing that happens is it stretches irreversibly. Everything that happens in the plane. And then I take it out of the plane and it looks like that. Now, hey, yesterday we heard, both by Alex and myself, that you can bend things by making the upper layer longer than the lower layer and then the lower layer longer than the upper layer. But seriously? 6 generations? It doesn't make sense. It probably is not the strategy. And indeed, it is not the strategy. And we can show that everything you could see here actually comes from a 2D input. All we do is we differentially elongate this plastic sheet away from the boundary. Pieces that are very close to the tone edge are stretched tangentially a lot, and then this tangential tension diminishes as we go into the bulk and goes down to 0. This induces a hyperbolic metric, a metric of negative Gaussian curvature. And we saw that when it is embedded, gives rise to saddle shape objects. Then why do you say frustrated? Well, the reason I say frustrated is because we did not break the up-down symmetry. If I cut a tiny, tiny piece of this thing, it doesn't know up from down. It doesn't want to bend. Any configuration which is bent essentially costs its energy. So now you have this competition between not wanting to bend and having a metric which necessitates bending. And it's this competition that makes the resolution so fascinating and so marvelous. If you do this very, very carefully, as done in this paper, and you tear something which is essentially 11 microns thick, this is kitchen saran wrap, you can get 6 generations of self-similarity of this shape. And I sometimes get these two mixed. I think I got it right here. But I think this one is a toned plastic sheet and this is a beet leaf. but it might just as well be the other way around. We see this mechanism repeating in nature in many, many different cases. It's hard to prove it when you're talking about the plant kingdom, because plants have this plasticity that if you leave them curved enough for a prolonged time, they just assume that shape eventually. So they evolve into the shape they get. But the way the shape formed, you can prove it was by metric prescription.
Completely does this during development, or when the leaves are about to come out of the bud, they already wrinkled in this fashion, or it's a different mechanism, different history than the corn plastic. Seldom.
Yes. So surprisingly, most of what's happening is that gives rise to the shape is cell expansion rather than division. Cells in plants can expand 100-fold in area, and it's differential cell expansion. For the beet leaf, I don't think we have proved it, but for an eggplant leaf, we have. So this is a shape that was assumed in the cell expansion period outside the cell. Arabidopsis leaves, also some of them show this. I know that some leaves are born very crinkled, and I don't have an explanation for that now.
And the two insects, one is the diminution of the out-of-plane height of the circumference distance to the edge. That's the upper right curve there.
That's the normalized length measured along the crack. So this is how much this thing has elongated with respect to unity. Way into the bulk, it doesn't elongate at all, and most of the elongation is here. And the Gaussian curvature is essentially the minus second derivative of this guy.
And the log plot on the top middle is what?
That's the amplitude of the wave number you see on these undulations. Yes.
So in this plastic sheet, you sort of have to get the geometric frustration you need to stress it, the sheet stretches plastic to be less than the stress at which the crack propagates. Because if the crack propagates at a lower stress, then all this.
Yes, brittle material don't show this. This is unique to ductile material, indeed.
Because I need to increase the area of the sheet.
Yes, most certainly right. Last of all, we discussed this guy yesterday. This is a seed pod, and we saw that its architecture was such that it wants to curves in both directions, but we showed that you could achieve this while making minimal metric deviation. So metrically, it would like to be flat. Curvature-wise, it would like to have two opposite curvatures. That's the mirror image of what we just talked about. So this is this guy. Now, there's one way of figuring out if things are frustrated, and that's to cut them up. It's a bit destructive, but it's very insightful. So you take the seed pod, and you're not sure if it is under a state of residual stress or not, and you insert notches. And if the sheet continues to deform after you added these degrees of freedom, it can actually deform in ways it could not before, as it has here, then it tells you that the contiguous portion was straining itself, was in a state of self-stress, if you'd like, in a residual stressed state. This sort of tells you who's the driving mechanism. These are pieces from the same seed pod drying up. And you see that the smaller, the narrower the ribbon, the more twisted they become. We're going to come back to this kind of images later on. This one is obviously closer or less closer to what we'd like to do, or closer to its reference metric in some sense than this guy. Towards the end of yesterday's lecture, two participants approached me and said, we have a history, we have background in GR, and we really, really like this approach to elasticity. Why don't more people use it? So it's not a new method. It was actually introduced way back in the 50s, and these are monographs by a Japanese group. The monographs go by the quite presumptuous name of Unifying Study Basic Problems in Engineering and Sciences by Means of Geometry. It's a group of 16 Japanese that decided they don't want peer reviews, and they're just going to publish in this group. And Kazuo Kondo, which was one of the heads of this group, wrote that it is very strange that the first practical field of application of Riemannian geometry was not a theory of elasticity, especially that of residual strains. And he blames general relativity for giving a metaphorical appearance to Riemannian expressions and banishing it for a time from the attentions of engineers. The other face of that is because of GR, we have all this machinery that we learn in undergrad, and we're able to cope with these expressions. So it's not a new idea, but it has not been used in the literature for a very long time. It's being revived. A more modern introduction to these notions can be found in a book by Sierlet, which is called An Introduction to Differential Geometry with Applications to Elasticity. And most of the notions of geometry I talked about yesterday and will today are found in here. Okay. Questions so far? Yes. So it's not that you get geometric frustration into these things deliberately. It's just that you prescribe one thing and you're not careful to make sure that everything else follows it. So I did the tearing, and in the tearing process, I did not break the up-down symmetry. Essentially, I did not differentially elongate the uppermost surface and the lowermost surface. That means that locally, this thing doesn't want to bend. If it's bent up, this guy is longer than this guy. So this is the beginning. But on the other hand, I elongated it differentially, and in such a way that I can calculate and show that it has to curve out of the plane. So now I'm telling you, this guy would like not to curve out of the plane. This is the curvature, whereas the metric necessitates curving out of the plane. And that generates the frustration. What? Most plastic deformations will show residual stress to some degree or another, because the chance that they will not is very, very small. We saw yesterday that something very special has to happen to a metric in order for it to be flat. And when you're talking about thin sheets, that also holds. Now, if you just cut it with the scissors, probably just get 2 pieces of the thing you had to begin with. And if that one was not frustrated, then the resulting thing is not frustrated. But the minute you induce deformations, chances are that unless you're very, very careful, it's going to generate frustration. Yes. The intrinsic deformation which you induce in the material depend on the rate in which the deformation happens, and essentially it changes the wave number and everything else. But it changes the metric. It doesn't change the fact that you still don't break up-down symmetry. Yeah. I don't think so. Do you have a... So here, the reason the elongation is focused to the boundary is because the state of stress in the boundary is very, very large. You focus all your efforts in there. It's not that you excite something and it lives on the boundary. You invoke this deformation only on the boundary, and that's where you see it eventually. Okay? Okay, so I want to recap what we had from last time. And in order to save us time, it's here. What do we have here? The metric is the tool with which we measure distances. There's the Christoffel symbol. It's the connection of the metric. It's the guy who tells us how to propagate directions in the metric. It's the guy who teaches us how to differentiate. All the geometric input of the metric is essentially encoded in this structure, which is called the Riemannian curvature tensor, and it tells us how non-commutative are second derivatives, or essentially what happens to vectors when you parallel transport them along a closed loop. If we now judge this thing, the Riemannian curvature tensor, in the very, very narrow sense of embeddability in flat space, we have the following. If we're talking about a 2D manifold in a 2D flat space world, then this guy would give us just one condition in the form of vanishing Gaussian curvature. That's what we have to satisfy for an arbitrary metric to be embeddable in 2D space, essentially on this countertop. However, if the metric is three-dimensional and we try to embed it in three-dimensional space, then we have 6 conditions from this guy. Then we examined something which was different. So this is 2D in 2D and 3D in 3D. And then we examined also 2D in 3D. We have a surface. It no longer suffices to tell us what is the metric in order to tell what the configuration of the surface in space is. You also have to give me the curvatures of the surface. Those are not independent. We saw that there are different ways. One of the members of the audience asked if we could formulate these conditions as coming from an integrability condition. The answer is, of course, yes. If you have d alpha, d beta, r equals gamma, gamma, alpha, beta, d gamma r, plus b alpha, beta, hat n, d alpha hat n equals minus a gamma delta, b alpha delta, d gamma r. So this is a set of equations for the normal and the tangent vectors. So this is the first derivative of the tangent vectors. And the existence condition for a solution for this are these guys. Another offer that was given by David Nelson was that we could think of the differential for the normal as given here as some f1 dx1 plus f2 dx2, and ask what is the condition that this is a total differential. This would again give us this thing. So anything you would like to do which is constructive essentially would get you the right answer. What I chose to do was to think as this thing as an abstract surface and make it into a 3D solid, and as you know mathematicians do, and a 3D solid I have already solved. So a G metric in 3 dimensions is a 2D metric minus extrusion along the normal direction. If this is alpha beta, this is alpha beta. We show that these are vanish, and this is unity. Okay, so this is a 2D matrix with this x3 variation. We asked when is this flat, and we got this answer again. So all these guys led us to this specific answer.
I missed this condition. So this is a covariant derivative?
No, these are not covariant derivatives. These are actually what you get from the embedding equations of a surface in 3D. So I take the surface, and I have 2 coordinates. X alpha is actually x1 and x2, but r is 3-dimensional. So now I ask, what is the second derivative of r? It has a component in the tangent space, which is just given by the Christoffel symbol.
That came into the long derivative when you differentiate.
Oh, I didn't do this yesterday, actually.
Right. No, the first piece is the thing that came in.
Yes.
That
moved me around.
Derivative
Exactly.
The tangent space was.
Yes. This is exactly this.
Oh, I see. But then it can also come out. Okay.
Yes, and this is now it can come out of my manifold along this direction because it's embedded in a higher space, and this is what we get. This is what I did yesterday. These are alternative methods to get the exact same thing. Okay. Let's go on the other side of the board. What we're going to do next is we'll look at elastic problems. We will start with one elastic problem, which will be 2D in 2D. We will use a compatibility condition, and then we will go to the richer world of 2D in 3D. We'll embed surfaces, but there again we'll be frustrated. So how am I doing in terms of the recess time? Okay, I think we're going to make it. Okay. So there's a slight problem with taking the notions of elasticity we had learned about and implementing them directly to this kind of a system. And what's the problem? So we saw that the classical way of defining a strain was to take the displacement tensor, displacement vector, which takes where you started from and subtracts that from where you ended up, and then write in terms of gradients of this form what you have. That sort of assumes that you started somewhere, that there's a configuration in which you are at rest, with respect to which you measure strains. What do you do when you don't have such a configuration? So the answer to that can come in a variety of different reasons. I think the shortest way to go there is the following. What Tom Lubensky taught us is that this expression is the same thing as writing half the metric tensor of the present configuration R minus the metric tensor in the reference state. Hey, these are tensors. This is a tensor, this is a tensor, this is the reference state tensor. I can change a coordinate family as I please. So I now use, now I can use a transformation from my initial variables to some arbitrary variables, x prime, and I rephrase epsilon and g and I. What do they look like? So epsilon prime ij, there's a g prime ij, and this guy becomes g bar prime ij. Can everyone see here? No. We'll have to work with this. So this is the expression we have where g prime ij is essentially lambda ki lambda lj g kl. So this is the standard tensor transformation rule, and this also tells us that g bar prime was lambda ki lambda l j, this is ij, I kl. Yes.
Sorry, can I just ask? I'm not exactly sure what we're doing here. Is that what if we don't have the two configuration?
We don't.
What does that mean? I mean, why isn't it just, for example, x equals r, u equals 0?
Because we're going to have rich solutions even in the absence of external forces. In a standard elastic system, if you just set it put, it does nothing, indeed. All the richness comes from the boundary conditions, from exciting waves in it, comes from different excitations of it. What we will do is one level below that, we will examine unconstrained objects, because in our case, even the unconstrained, unforced systems will display some non-trivial solutions. Okay, but in a standard system, it's the boundary conditions that give you the results. Okay, so what I wanted to say here is that now I have something that looks like this. A strain tensor with respect to some other coordinates I'm not used to, but I might just as well use them, is Gij minus some reference metric ij. If I use this formulation as taken from, as a reformulation of this Landau-Lifshitz sort of version, then I know the following things. This is a metric of a configuration of an elastic body in Euclidean space. The Riemann curvature tensor of this guy has to be zero identically. This is where my sister started from. It was also flat to begin with, so it also has to be zero. This is where we change things. We say this guy could be arbitrary. We ask, what if we formulate all of elasticity, and it can go back to square one, and say G, which is going to be flat Riemannianly because it's going to describe the configuration of an object in our space, determines the configuration of the object uniquely up to rigid motions. Everything else is encoded in the tendency of the material. Metrically speaking, it's encoded in a reference metric tensor. It is locally what the object would like to assume. So now we have a local tendency of the material, and that is contrasted by the fact that it has to be satisfied by something which can't satisfy this. This is where all the richness is going to come from. And we can now formulate this thing in a tensorial fashion.
In other words, the G bar can't be represented as
Exactly. As long as it is flat, I know that there exists some lambda transpose lambda. You could cook up a lambda transpose lambda. However, that lambda would not be a gradient of a function. So you could cook up something which we could call a virtual gradient, but it's not going to be really a gradient of a deformation. So there is a square root because this is going to still be positive definite. It's just that this thing is no longer a gradient. I think this is a good... Every G bar is going to be a different system. For G bar, it's completely different problems. But the thing is, now you can formulate things with respect to the reference lengths or the reference metrics such that you're going to be completely oblivious to the underlying coordinates you use, to the underlying history. All you're going to care about is essentially the Riemannian curvature of this thing. And everything else is going to drop out.
Most of the examples that you cited, wouldn't the bending rigidity external curvature tensor come in explicitly, so you don't forget that you embedded
3D in 3D or 2D in 2D. I'm now in tight embeddings.
Oh, okay. So we're not talking about 2D and 3D.
We're not talking about 2D and 3D now. We're just talking about tight embedding. What I'll do soon is I'm going to use that extension to take slightly thick surfaces and make those into 3D objects. But this is tight embeddings. This is 3D in 3D and 2D in 2D.
So, I mean, to connect to Tom's lecture, so non-trivial G bar is like encoding random for spring length?
Exactly. So now if I spatially vary the spring lengths, then I get this thing which is going to be a non-trivial G bar. And all the response of the material is going to be dependent on that.
I think it's also like putting a non-trivial space-dependent vector potential in a superconductor. Non-zero curl is a magnetic field that distorts the underlying space. It's a simpler problem, actually. But
Because it's a scalar.
yeah.
So it is some extent, it's, yes.
There's a lot of
Yeah.
mathematics.
I think the key to all these problems is that the input does not map trivially to a configuration. And what we're going to have to do is labor in order to get the configuration from this thing.
The point is that Gij cannot mimic your
Yes.
prescribed G bar.
Exactly. So is this 50 minutes now? I think it's a good time to have a 5-minute stop, and then we'll take on after that.
So Gij cannot
to follow G bar. Yes,
Won't be able to follow G bar, and those are the built-in stresses that are
exactly.
intrinsically.
Just to ask really quick, different lambdas transforming G prime and G bar prime?
No, they're the same lambda.
They're the same.
So what I did is I took this that expression and I changed coordinates. When you change coordinates the same way to everyone, to this guy, and this guy. That's what makes, you know, tensorial equations hold in every coordinate system. What you do to the one, you do to everyone else.
So now in principle you have two metrics on the same manifold.
Yes.
So one's a reference, which is what it wants, and one's via embedding.
Yes,
Yeah.
exactly.
So
And this is the game.
How do you so which metric do you use to change indices and to shift?
Patience.
Sorry?
Patience.
Okay.
Yes. In short, the reference.
Okay.
Okay, you want to formulate a problem in which there's a whole chunk which is going to depend only on the material properties, and it's going to care about the configuration only through the metric. Okay? So we can formulate the elastic problem this way or the other way. The way I like best is formulate everything in terms of the reference. So we're going to need to layer or lower indices. We're going to do this with a reference. And this will give us a very compact way of writing
But
things.
does it matter? I mean, linearized level it won't change anything. But
Most of the things here are non-linear.
yes, this is
You care about the curvature. You have to go to non-linear orders. Otherwise, it's impossible.
No, but because what I'm asking is, regular elasticity we always tend to frame it from the reference point of view.
Yes.
But if you look at, say, fluid membranes, then the curvature.
Fluid membranes don't have a metric.
Yeah, they
Don't
they
get confused. So I cannot assign.
No, but they don't have a reference metric, but they still have an embedded metric.
Exactly. Yes. They don't have a reference metric.
Yeah. So they're done in the final configuration, not in the reference state.
There is no reference
Yeah,
state.
there is no reference state.
Yes.
Exactly. So here, but here you have an elastic sheet which has a reference state, but you're also bending it. So the bending curvature terms, it doesn't matter whether they're counted on the reference state. I mean, calculated with respect to the reference state, or it doesn't matter whether you calculate with respect to the final state.
Say again.
The bending terms.
Yes.
So if I have like the mean curvature squared in the energy, does it matter if the energy is calculated on the reference metric or on the final metric?
If I have a solid thin sheet, I would like it to do things in the reference frame.
Okay.
It's a choice. You have to understand it's a choice.
All right.
That choice will influence what are the physical structures you work with.
Okay.
I'm working with the reference state, with a reference system. That would give rise to the second Piola-Kirchhoff stress tensor. If I would work with another reference metric, or if I would weigh things with respect to area in the deformed configuration, I mean, what do I take for dV?
Exactly. That's my question.
If I take
Root G bar or root G?
or if I take G bar.
Yeah.
This would give rise, this is what I do.
Yeah. Okay.
It gives rise to the second Piola-Kirchhoff stress tensor. This would give you the first Piola-Kirchhoff stress tensor. It's legitimate. It's another way of walking. You can use it. But it's a choice, and you have to make this choice once and for all. I just think it's most convenient to have just one canonical geometry you use, which is the reference, and everything else is the result.
So this is a stupid question, but going back, essentially, so I have this right in my head. If you were to draw a square grid on this
Yes.
and deform it,
Yeah.
so which G is unchanged in there and which G is
Okay.
the curvature?
This is dodgy because this is 2D in 3D. Okay? Your tension
Okay.
is going to generate a non-Euclidean 2D metric.
Right.
You would follow these squares. You would see that they hardly deform along this direction, but they differentially elongate along this direction. This was one of the plots David Nelson asked about. You measure distances there as a function of distance from the edge, and you get something that looks like this. The closer you are to the edge, the longer you become. So this is essentially the metric. This is how distance is deformed because of this irreversible deformation. And now You say, well, how do I translate that? Is this Euclidean? Is this non-Euclidean? What do I do? It turns out that you take, if this is phi, you take second derivative of this guy, slap on a minus divided by itself. That gives you the Gaussian curvature of this thing. So this is a direct connection. You know, you do this thing, you differentiate elongate, it tells you if it's flat or not. Okay?
Can I ask you a quick question?
Yeah, let's just move there so we can wipe this board. Yes.
Just to make sure that I understood it right. So the G is the flat space, the metric of the
Yes.
flat space, the Euclidean. And is G prime the because it's arbitrary, is the knob you turn to fit the curvature you see?
Okay, so what was happening here is people give us everything in flat terms. I wanted to formulate things that they would look general. You can erase it. We can erase it. Let me help you.
Erase them all? Okay, thank you. Thank you so much.
Sure. So you wanna? I want to.
He said to erase it.
I asked to
Okay,
erase
I
it.
figure people still looking at it.
Yeah, I have more writing.
Okay.
Just hate to. You don't see well. So G prime was just to make the compatible thing look general. That was the primes. The general thing, which we will now define, is defined with G bars, and that's going to be quite.
But then you said G bar is arbitrary, which means
It's not arbitrary. I'm going to define it, but now in this theory, it's going to be
but
whatever
you
I'd
try
like.
to define it in a way that it describes the curvature of
Yes.
your surface, right?
Yes.
Okay.
The reference curvature. Okay. Let's go on and take it from there. Okay.
And could you upload your notes?
I will. I was too busy copying my notes to my notes to make sure that I give you a lecture.
The stuff that you send me, you know, for your PDF.
Yes.
Can I just upload that, or have you made corrections?
No, actually there is a correction. The tall guy from yesterday gave me a few corrections, so they're already incorporated.
So
Wait
I
with
won't
it.
upload until you give
Yes,
me the
yes,
corrected version.
yes, please.
And also, could you upload the pictures?
I will.
Because they're not
Okay.
Sounds good.
So let's continue. There's a notion in elasticity called hyperelasticity, which says it's the general class of elastic systems in which the elastic energy derives from a local energy density, and that energy density depends essentially on the configuration only through the strain tensor, but all the other things it depends on are material properties. So the only place where your different configurations contribute to the different energies are here, and everything else essentially encodes the materials properties. We just said that what we're going to look for is an embedding which is going to be flat, and we know that flat embeddings are unique up to rigid motions. So if I know the metric, I know the configuration of my object. So we're going to replace this guy with a metric, and everything else is going to be material properties. In particular, in every point in space, there will be one metric such that if G is going to be equal to that metric, it's going to be associated with zero energy. That is the reference metric. This is metrically what the object would like to do in that point in space. Now we can essentially recap this notion by Truesdell to a general object, to linear order. And when I say linear, I mean linear constitutively, not geometrically. So we still are good for large rotations. Yes? In particular, regular elastic materials are hyperelastic. In particular, regular elastic materials are hyperelastic. Okay, this is a notion that extends that notion to a whole class of constitutive laws. It does not capture viscoelasticity. It does not capture history dependence of any sort. So it does not capture long distance correlations. There's a whole variety of things it does not encapsulate, but Landau-Lifshitz elasticity, it does capture most of it. The first few pages at least. This can be written in terms of a strain, which now would be half the difference between metrics. This is the one we realize, this is the one we want to be. Remember that when we're doing things in tensor notation, we have to have one metric, and only one, with which we lower and raise indices. It's going to be this guy. So G bar is used to raise indices. And for volume measure. The later is actually a choice. I'm going to do things per unit volume of the reference state. That will lead us naturally to the second pure Kirchhoff-Strass tensor. We could have done it per unit area, per unit volume of the resulting configuration. It would lead to the first. To leading order, this energy density is going to be quadratic in epsilon. This is a tensor with two legs. How many different quadratures does it have? I essentially have to close four legs one another. The tensor is symmetric, so those don't matter. How many different terms can I have? Okay, so there's one term is take these two legs and contract them with these two legs. Okay? So these are two tensors. How many of you lost me? Suddenly I hear this here. What? Legs? Okay. Indices, yes. I'm talking indices. I'm just thinking graphically that if this is the tensor and it has these two legs, and this is another tensor, this is I, this is J, this is K, this is L. So I have a general relation, a linear relation that makes these quadratures is essentially A, I, J, K, L. This is the elasticity tensor. It has all the Young's modulus, it has the Poisson ratio, it has everything in it. Other than that, it's composed of reference metrics. And then I'm slapping that on epsilon ij, epsilon kl. And I ask, how many different terms do I have here? That was my question. And it amounts to asking how many different ways I have of connecting these guys. So this is one way of connecting them. And another way of connecting them is this way. And all the other are essentially these two. I allow A to depend on G bar. This is essentially how I raise and lower indices. I don't allow it to depend on G. So A contains a lot of material properties. I use it to raise the indices of epsilon. So this is essentially raising the indices, and it's a material property. Yes, exactly. And you remember G bar indefinitely. Yeah. Okay. I don't allow. Okay. Yes. So this assumes the underlying Riemannian structure. In particular, I don't have preferred directions, and I don't have any of that sort in my geometry. This is the Young's modulus. This is the Poisson ratio. This is epsilon ij, epsilon ij. It was the guy that connected the two tensor. This is epsilon kk. It's the trace of epsilon squared. Note that when I take the trace, I first have to take one of the legs up. I do that with a reference metric, and then only I can contract them. We could understand one of these guys as being g bar kl epsilon kl. Okay? So L was raised with this g bar, and then it was contracted. So this is what this means, but it allows you to write things very compactly.
Why are you raising with G bar as opposed to with G?
Because it's gonna, there's a conceptual reason, which is G is gonna be a part of the solution, and G bar is a material property. And I want to do things with respect to the reference state of the material property. And there's a more practical reason, because it makes things more convenient. To leading orders, you can do things this way or another.
This way it still remains quadratic
In G, exactly, yes.
And also, the point as a solution, but the solution might not realize G bar. Okay, but it doesn't matter. You just use.
It's not going to realize G bar, but it's going to attempt it, yes. Okay. When you do things this way, you get SI. This is still wet. You get Sij as the Fauchet derivative. So I differentiate a scalar with respect to lower indices tensors. I get upper indices tensors, just like we had with coordinates. That gives us Young's modulus over 1 plus nu, the Poisson ratio, epsilon ij plus nu over 1 minus 2 nu, epsilon kk g bar ij. This is the second Piola-Kirchhoff stress tensor. When we come to measure things in a lab, we measure real forces and we integrate over real area elements. Those are elements of the Cauchy stress. This is not that. Here, the forces are essentially derivatives of scalars, of potentials, with respect to the xi coordinates. So these are pointing along the tangent vectors with respect to xi. So these are generalized forces, and they're measured per unit of generalized area as defined by G bar. So now, because I'm using G bar for both of these, this guy is also symmetric. It satisfies an extended divergence equation, which is the covariant derivative with respect to G bar, Sij, plus, if you remember, I told you that the Christoffel symbol is not allowed in tensorial equations because it's not a tensor. But the difference between two, Christoffel symbol, happens to be a tensor. And this is, I think, one of the only places in space where you can get two different metrics which you would like to relate to simultaneously. And this is the object which corrects this thing. So now we can actually come to solve things. And when we will solve things, yes, please. No, it has both legs in the same space. The second Piola-Kirchhoff stress tensor has both legs in the reference. Both legs are Lagrangian. It's the first that has a Lagrangian and an Eulerian leg. Okay? Okay. So to some extent, what we'll do next did not require all this machinery, but I think it's a very elegant problem which exemplifies a lot of the notions here of residual stress. We will consider a case in which we are only slightly perturbing a flat configuration. So the metric is going to be almost the flat metric, and the reference metric is also going to be and the reference metric is also going to be almost flat. So not only these things are flat, we're also using the Cartesian coordinates on them, or the almost Cartesian coordinates on them. And what we'll do is we'll formulate this elastic problem with a non-Euclidean G bar and try to solve for G and linearize with delta. Okay? So when we're taking only things to first order in delta, all the exotic things about the divergence equations vanish, and we end up with this standard notation. This tells us that we can find a vector potential phi such that S11 equals D2 D2 phi, S22 equals D1 D1 phi. Notice the anti-symmetry. And S12, I can't really change the numbers, so I'm just might as well change the sign. You can show that any divergence-less tensor field can be written in this form. Okay? Now, because everything is almost flat and almost Cartesian, raising and lower indices is performed with the unit identity. We're keeping only things to linear order. We can also calculate, yes? Yes, or as we'll see next, a crystal deposited on the surface of a sphere. Something that would like to be flat in a curved space. Mm-hmm. Yes. Only if I'm now talking about embedded objects. So if I'm 2D in 2D, I don't expect those. If my world is 2D, I don't expect those terms. If I'm 3D in 3D, I don't expect any extrinsic terms. There aren't any extrinsic terms. To be the world. The minute we're gonna get into getting into that structure, then we'll have to go to embedded objects, and then we will have exactly what you say. We'll have extrinsic forms, we'll have curvatures, for example, which we don't here. So, but that goes once we consider the more extended world. Okay. The Gaussian curvature of a metric is usually a very nonlinear function. But as I told you, we're looking for something which is almost flat. And as such, it has a linearization. Its second derivative with respect to the first variable of G22 plus D2 D2 of G11 minus twice D1 D2 G12. One can also show that this, if we would take now, for example, a simplifying assumption that the Young's modulus equals 1 and the Poisson ratio equals 0. We can relax these assumptions, but it's going to make the calculation a bit hairier. But if we keep these assumptions, can I do this? Yes, I can. If we keep these assumptions, we can show that the elastic solution to this results in the biharmonic equation for phi. But it's not going to be harmonic. It's going to have a source term which comes from these guys. They're essentially going to be k bar minus k. This is the curvature of the reference metric, and this is the curvature of the embedded space. I could take a piece of a sphere, a small piece of a sphere, and flatten it on the sheet. flatten it between two glass plates, and make it live there. Now, if this tiny spherical cap was elastic, the amount of elastic energy it would have in that configuration is given exactly by these equations. We can show, we can solve it in axially symmetric coordinates. I want to give just one solution. Not one solution, just I'll give you the final form of it. If we consider something which is going to be very long and narrow, so this is long, L, it's narrow along the width. And when things are very long, we would like to say that if this is x2 coordinates, then things don't really vary much along the x2 direction. So you can extend in kind of in a fine solution for this thing. In particular, I would expect all terms of g not to depend on x2. You have this in my notes. The final result says that strains are going to roughly look like this. They're going to be, and they have to average to 0. And the elastic energy of a system that looks like this looks as follows. It's delta k squared, width to the 5th, times length. You can understand this following way. The strain is quadratic in W, and then strain squared gives you W to the 4th, and then you integrate it times W times L, gives you another W and another L. This delta K comes from each of the strain components. This is 2D in 2D, yes. So there's no thin sheets here. There's no thickness whatsoever. These guys never heard of thickness. Yes, so, but these are Riemannian curvatures. So this is Gaussian curvature of the reference configuration, Gaussian curvature of the realized one. If I'm embedding a spherical cap onto flatland, then this guy is constant and positive, and this one is 0. If I am embedding a piece of flatland on a spherical cap, I have the other way around. This one is going to be constant and positive, and this guy is going to be 0. And guess what? This guy doesn't care. Let's look at two limits for this solution, which is affine. Let's do it there. The given energy is delta K squared W to the 5th times L. Let's fix the aspect ratio. Which is essentially L over W, W over L. It's called alpha, and that's constant. That tells us that W equals alpha L, and that tells us that this thing reads delta K squared, 2 alphas. Now I have only 3 W's remaining, but I made 2 of them into 2 L's, so I have L to the 3rd. Okay? This is area to the 3rd. This is supra-extensive. That means that if I now take my slab and make it twice as big, the elastic energy associated with embedding that object now has grown to the power of 8. The elastic energy per unit area on average has gone to be twice what it was. This is very, very peculiar. Now, of course, we can show that if we do constant W, constant width, is going to lead us to something which is going to be delta K squared W to the 4th times area. So here the elastic energy is extensive, and what we see that the longer you grow, you add essentially elastic energy proportional to the area. You care about the aspect ratio of your solution, and you care about how big your system is. I remind you, these all were done in the context of uniform frustration. So the frustration is uniform, but the residual stress builds up the bigger the system is. And this is the main difference we should think of between residual stress and geometric frustration. W is the width after the distortion. But we could, to a large extent, we could think of them as differ only by higher powers of delta. W in particular, in this case, we could W in this case of Poisson ratio equals 0 is going to be identical in beginning and end of the deformation. Okay. The resolution is very non-uniform. The resolution of the frustration is very non-uniform. In that sense, the solution is non-local. The problem itself, everything about the elastic problem was local. So I want to do the following. This grows as area to the 3rd, so it starts very flat and it goes this way. And this begins as area to the 1st power. And this is elastic energy, and this is area. When we first nucleate these things, which are very, very frustrated, they will grow isotropically with a constant aspect ratio. And then they will hit a boundary, some length scale or some area scale, after which they would like to form something which is narrow along one of the directions. So this is a filamentation process which is driven solely by frustration. So I guess in the audience there's a graduate student or a postdoc of Vinny Manoharan, and what I want to show you is a work from his lab that David Nelson also was working with them. And this is the following. It's colloidal particles on the surface of a sphere. They're confined to live in the surface of a sphere, but they would like to make a perfect hexagonal lattice. And I didn't include this in, but you see that when they nucleate, they make very small isotropic patches, and then they reach a typical width. And then they make these ribbons of a relatively constant width. And now they meander and go around because no one told them they had to be straight, but they make filaments of a certain width. And that is given by the geometric length scale. The geometric frustration in the problem, the fact that I gave you a flat sheet and I told you you have to live on a positively curved surface, necessitated the presence of residual stresses. But the two are not identical. In particular, this guy is a local property. It only cares about the local geometry of your system and its reference geometry. And this guy has a global dependence. It cares about the aspect ratio. It cares about how big your system is and other things of that sort. One may ask legitimately, why don't we see this everywhere? Why, or to some extent, what made this system very, very special? So what made this system very special is the fact that their interactions between the colloidal particles were such that they were so short-ranged that defects were completely precluded from the system. Particles rather remain in the melt than make a 5 or a 7 defect in this crystal. And that tells us also why we don't see this commonly. What happens is that what I told you now is a way of resolving the frustration which was very smart. You were as close as possible to the reference metric. But imagine if I was just dropping these things onto the surface of the sphere and I was allowing defects. At a certain stage in time, you would acquire a sufficient amount of curvature to make a 5-fold defect. And once you make that, that accumulates a lot of curvature. And in addition, with all the rest of the guys around it, it approximates your surface. So that would be a very, very expensive but local resolution of frustration. Okay? So if we're thinking in terms of something that is energy per unit area, it's going to be very, very, very expensive to walk this way. But it turns out that the majority of systems do allow local resolution of frustration. All these smart strategies appear mostly when the systems are marginal. Questions so far? Yes? Yes. It does. It does, but everything I just showed there, you should judge with respect to the almost flat setting. Okay? If we go to a hyperbolic metric, for example, an area grows exponentially, that's going to be, the elephant riding your system. You're going to see primarily that. But in the almost flat setting, which is to some extent more interesting, you should just throw that out the window. Questions? Let's go on. Sorry. Now you may remember that when I did the derivation of surfaces embedded in 3D, and I showed the compatibility conditions, I did that by slicing my solid, which is now thin, yet three-dimensional solid, into layers. And I had one coordinate going along across the layers, and that was this coordinate, and I used arc length coordinates. And you can always do that. And that's going to be perpendicular to the layers, meaning all these guys are 0. And everything else is encoded by the geometry of the layers. If the layers' geometry vary across the thickness, say the outermost layer is very long, the innermost layer is very short, it's going to have curvature. And things also happen spatially, so the layers could have geometry that changes spatially. So we said that this was A2D plus x3 or minus 2x3 b. Yeah, I want to write bigger and somewhere here. Say we have a metric of this form. It's going to be G2D of x1, x2, and x3. I can extract from that, that's G bar, sorry. I can extract from that A bar, which is now has only 2 variables. It is what G bar says when you read its value on the neutral plane, on the center, on the mid plane of all these layers. And B bar is going to be minus half the derivative of G the difference between the geometry of the layers. You can think of this as averaging out the 2D geometry of the layers, and this guy takes the derivative, the differences between the geometry of the layers. This is going to get 2D geometry. This is going to give us curvatures. And now we're in the realm where we can formulate those equations which were written previously in terms of a 3D functional that had G bar, and material properties, into something that would have just the metric, which is now 2D, the reference metric, which is 2D, the curvature, the reference curvature, and materials properties. And we know that A and B, which is the metric of the surface I have, and B is the curvature of the surface I have, these are the results. This is what I see in real space. If these two are compatible with one another, compatibility in the sense written up there, then I can reconstruct from them a surface uniquely up to rigid motions. So they define a surface. I can use them as variables to describe my object. Now I have two independent tendencies: the metric tendency, the reference metric, and the reference curvatures. And as we saw here, I can have a case where I have B bar equals 0, no curvatures whatsoever, but a non-trivial A bar. And I can have the other way around. I can have a completely trivial A bar, just identity would be flat, and non-trivial B bars. Questions about that? My notes are there. Let's just write down what this gives us. It's take two sheets. Take two sheets. One is tensed this way. The other one is tensed that way.
But such that within the sheet it's uniform.
Within the sheet it's uniform, and their average has uniform Euclidean geometry, but their difference has two principal curvatures. We're going to get to those soon. Okay. The elastic energy of the 2D object is given by a stretching term and a bending term. And they're all integrated with respect to the reference metric dx1, dx2. The stretching term is linear in the thickness. Essentially, you should think of this as many laminas. I stacked them all across the thickness. I took how much stretching in plane I had in each of them, and I summed it up. That's linear in the thickness. There's going to be an A-twiddle, an elasticity tensor, and a metric difference. The bending term is going to be cubic in the thickness. It's going to have the same elasticity tensor, and it's going to be, again, quadratic in the curvatures. The elasticity tensor for 2D reads Young's modulus over 1 plus ni half A bar alpha gamma A bar beta delta plus A bar alpha delta A bar gamma beta plus Poisson ratio over 1 minus Poisson ratio A bar alpha beta A bar gamma delta. our elastic energy has two distinct contributions. One comes solely from stretching things in 2D. One comes solely from bending things. And when I come to define an elastic problem now, what I tell you is I have a material and it has some given A bar and some given B bar. And your task is find me an A and a B that minimize this elastic energy for a given thickness with respect to these A bars and B bars, but such that A and B satisfy the compatibility conditions. Now, this is slightly misleading in the following sense. Everything here is written as quadratures. So it looks like, naively, we have 2 degrees of freedom, each of which is quadratic. In particular, we would expect each of them to carry equal amounts of energies for the frustrated system. But all the nonlinearities actually reside in the compatibility conditions. And what we will see is that for very large thicknesses, this could have no energy at all. Whereas for very small thicknesses, this could have almost no energy. And in the interplay in between the two, almost in no space in time or in thickness, do we see a case where the two are comparable. And the reason is because the zero energy level set of this guy and this guy, where the zero energy level set, meaning A equals A bar and B equals B bar, have zero overlap. I can simultaneously satisfy this and this. So I want to give you an example. The first example of a non-Euclidean plate, which is this thing. It looks like a plate because it doesn't want to bend. It's non-Euclidean because I gave it a non-Euclidean geometry. It's this thing. You endow this thing with a hyperbolic geometry, but all laminas, all layers behave the same. Let's go with this. You can do this thing in a more controllable fashion. How do you do this thing in a more controllable fashion? You can take something which is a hydrogel which is environmentally active. Okay? I have a gel in a high concentration and a low concentration, and I generate some mixture of that gel, and I let it cross-link in a cell such that all layers have identical structures. Nothing varies across the thickness of this thing. But between the center of this thing and the boundary, I inserted some gradient, some structural gradient in this gel concentration. It's environmentally responsive, meaning that when I heat it up, it's going to shrink. And its shrinking ratio depends on if it's dilute or dense. In the densest regions, it's going to shrink very little. In the most dilute regions, it's going to shrink a lot. So when I take this thing and I shrink it up, I can have a different metric. Only axial symmetrics metrics in this setting, but I can, for this case, have a dome-like metric. It's going to be positively curved metric. So this is a movie of the heating up of such an object which has the opposite, a hyperbolic metric. So you can see it's very dilute at the center. It's going to shrink a lot in there. It has a very dense exterior, so it's going to shrink very little in there. And you can see not only the ruffling, but the fact that it went into a saddle shape-like. And now we can cool it down, and it rehydrates, and it drinks everything up. But it's very important to say that what we program here is A bar. In this case, it could be something that looks like a hyperbolic cosine. Never mind the specific form. This guy.
Sorry, can you say again how you program the radial change in the concentration of the ingredients? How do you get the, so is it just freeze it in place before diffusion equalizes?
Because it polymerizes relatively fast and these things diffuse very little. So I can't get an awfully sharp gradient, but I get things that are very, very steep. put it faster or slower into the Healy shell? Yes. And controlling the viscosity of the fluids will matter, and controlling the polymer density would matter. Nowadays, there are more advanced systems. This, I just didn't have the slide in advance. You can do these things by photocross-linking. So you do this with riboflavin or some other UV photopolymerizing agent, and then you can have areas which are heavily cross-linked and dilutely cross-linked and would have the same effect. Okay, I think we're gonna study just at least this system to some extent. I think you wanna end here? Okay. This specific system we can endow with an elliptic metric. It's a hydrogel. It was produced in the exact same way, and now we can also simulate this thing. And what we get from simulation corresponds to a very, very large extent to the results we see in the lab. But this is a somewhat cleaner result, so I'm going to talk about this.
So
this is energy. What?
We're supposed to quit at 12:30. So we're 15 minutes old.
Okay.
I mean, if it was couple and you were finishing up, but I'm gonna. Otherwise, we won't be able to get back.
It's fine. Question. Yes.
One quick question. You said the task is to get the ATP.
Yes.
The energy and satisfy the compatibility condition.
Exactly.
So what is our compatibility?
A and B have to satisfy the Gauss-Mainardi-Peterson-Codazzi equations. They're the set of three equations that we wrote relating determinant of B, determinant of A, and first derivatives of B. There are three such equations, and that's what you have to satisfy. Yes.
So, back, a few steps back when you wrote the strain equals G minus G bar.
Yeah.
Can that formulation be related in any way to the multiplicative decomposition of deformation gradient?
Yes. So in the multiplicative definition, you have this virtual configurations, and then the square of that virtual configuration gives you G bar.
Okay.
Essentially, lambda lambda transpose of the virtual configuration gradient gives you G bar. What this thing does that the multiplicative system doesn't give you is it lets you do everything geometrically. The main advantage of using the multiplicative decomposition is if you're a mathematician and you want to prove existence. When you're trying to prove existence, working with metrics is very, very delicate because the metrics don't see inversions. If I take my material and let it go through itself, it doesn't see it. Whereas in the multiplicative decomposition, it changes sign for the gradient. Okay? So if you're trying to prove existence, you have very little luck working with this, and you want to work with a multiplicative decomposition. Other than that, this will shorten your life. Okay. Not shorten your life that way. It will shorten your the calculations significantly because it will allow you to do things in a covariant fashion very fast.
Okay. Thank you. I have a question about when you have a pre-stretched surface, and so you stretch one axis and then you overlay it on another surface.
Yes.
We could also see wrinkling because it would try to relax and the substrate over it.
Yes.
So what enhances the probability of seeing bending or bending in a certain handiness?
So this is a very complicated question in the respect when formulated this way because